let's say we have here a very harmless looking function, y equals to 2x plus 1. And let's plot this or sketch this function. Well, we have here the y-intercept, and this tells us the gradient is 2. So we know that it's going to cut the y-axis here, y-axis at 1, and the x-axis at negative half. And so this is the line. Okay, this is y equals to 2x plus 1. For any point which lies on the line, this line, it has to be be expressed in its coordinates in x and y. Say for example, say a point here is P, and P has to be expressed as coordinates in terms of x and y. But what if there's a way for us to express this in just in single variable instead of x and y? So we can do that. And here, now let me stress this, that by choice I'm going to let x be substituted by t, and t is any real number, and t is called a parameter. It's called parameter. Now when I do that, the y, or the function itself, I'm going to then replace or substitute the x by t. And so these two together, this here, this choice of x equals to t, and this substitution would then give me x equals t and y equals to 2t plus 1, because t is a real number. And then this set of equations is called a parametric equations. And this is called parametric equations of this straight line. It's the same as this function here, but in this kind of different looking form, and dependent on one variable, that is a t. And this form here, right here, is called Cartesian equations. Okay. Now, I suppose that the parametric equations of some certain straight line, it looks like this. And so okay, this is the parametric equations. Let me label this parametric equations. And we want to rewrite this in the Cartesian form. Now that's very simple. All I need to do first is to solve for t here by using this x equations, and I will have t x plus 1. Now really this is the first equation. Let's call this the second equation. Essentially we just substitute x into 1 into 2, and finally you have this. Of course you realize that suddenly the t is gone. No more t, and it's gone. Just simplifying this would give you this equation. So this is then the Cartesian equations of the straight line or the linear function, really. And this will be the parametric equation of the same function. This is amazing, isn't it? And now we're going to look at different examples where we're going to express from Cartesian to parametric. Now, say we have these quadratic equations. First is in Cartesian equations. Now, how do we express it in parametric equations, in the parametric form, that is? Now note that this side, the right hand side of the equation, really can be factorized as follows. Could be factorized as x plus 1 squared, right? So this is really is x plus 1 squared. So if I do this, by choice again, I'm going to let, okay, this is really by choice, say x plus 1 equivalent to t. Of course, t is a real number. So now I have x equals to, say, t minus 1. But as for y, the y is really x plus 1 squared. Since we are replacing, substituting x plus 1 by t, you notice that I can actually replace x plus 1, and I will get t squared. Right? Let me highlight this. This would be t squared. It will be y equals to t squared, and I have x equals to t minus 1, and t is any real number. So together, I could just take this away. Together, or rather maybe rub this, so you can see clearly this together will be the parametric equations of this quadratic equation. Sometimes we might want to find or derive the function, but the function could be, however, expressed in the form of parametric equations. And actually trying to re-express this into Cartesian form is not that simple. And so we want to use something like a shortcut. But to use a shortcut, we are going to use look at, to view a little bit from calculus, something from calculus, essentially the chain rule. And you probably recall that there's one rule that actually kind of relate to, or rather three variables. Say suppose dy dt, I want to relate y with x, and of course involving t in this case. So I may then write this as dy dt equals to dy dx times dx dt, and this is the chain rule. But however, I actually really want to find dy dx, so I can then rewrite dy dx as dy dt whole thing divided by dx dt. And this is how we can use this particular relationship to find dy dx if the function is defined in parametric equations as follows. So what you're going to do is this. Okay, so first we need to find dy dt, and this is dy dt, and you get negative 3t squared, and we have dx dt, that would be 4t, and finally your dy dx is really negative 3t squared divided by 4t, or negative 3 over 4 t. T is a real number. So